In our previous lecture, we were talking about equilibrium, the idea of reactions going forward and reverse, and finally where the two rates became equal, so that we had this point which we call chemical equilibrium, which we indicated was a dynamic situation. We also showed that we can have a qualitative, at least, description of the system in terms of what we called an equilibrium expression, which was in general products of the reaction divided by the reactants. And we indicated that in each case that the products and the reactants would be raised to a power corresponding to their coefficient from the balanced chemical equation. We also talked a little bit about the fact that it might be possible to subject a system at equilibrium to some change, and that the system will shift to offset that change. In other words, that we can affect where the equilibrium will actually occur. In other words, we can increase the amount of products, or we could decrease the amount of products that we might get by subjecting the system to a different set of conditions. And that study, of course, was carried out by Le Chatelier. And we looked at then some examples of applying Le Chatelier's principle, but I think let's just go back and kind of run over again these applications and see what predictions we would make. So we'll look at a couple more Le Chatelier's principle and applying it to chemical reaction. This is the reaction between gaseous water, as we can see here, with solid carbon. In an endothermic process, we're putting energy in to get the reaction to occur, and we produce carbon dioxide and hydrogen gas. The question is, what would happen to the equilibrium if I were to decrease the applied pressure? Now, we have to keep in mind that we're talking here about a closed system. By that we mean that everything is in one container. Nothing's escaping. If I'm going to decrease the pressure, Le Chatelier says that the system would try to increase the pressure. The only way it could increase the pressure would be to increase the number of gaseous particles. So we look at the two sides of the equation, and we see that on the product side, we have 2 moles of gas. On the reactant side, we have only 1 mole of gas. And therefore, if the equilibrium were to shift towards the product side, we would increase the number of moles of gas, and increasing the number of particles of gas would increase the pressure. So our prediction would be, keeping Le Chatelier's principle in mind, that if we decrease it, the shift would be toward the product side, increasing the amount of CO2 and hydrogen that would be produced before the new equilibrium would be reached. Let's look at temperature. If we were to increase the temperature, if we add energy, that's what we mean by increasing the temperature, the system is going to try to decrease. It's going to try to use up that energy that I add. And in order to use up energy for this reaction, it means that we would have to form more products again, wouldn't we? To use up the energy. If this one gets bigger, the only way we can get rid of it is give it to form more products. And so we would predict that as temperature is, temperature is decreased, not increased. So as temperature is decreased, the system would try to give the energy back, so we're lowering this, so we're decreasing this one. So the system would try to put the energy back, which it could do by going in that direction, the reverse reaction. So for this one, it's going to shift towards the reactant side of the reaction. We would end up getting less products at the lower temperature than we would at the higher temperature. Adding a catalyst. Does a catalyst affect equilibrium? Well, to answer that question, we really would have to go back and look at what a catalyst did to the activation energy barrier. So let's just sidetrack here a second, once again. If we recall, and this one, by the way, is an endothermic reaction, so we're showing something like this, okay? Now, a catalyst lowers the activation energy barrier. But keep in mind that anything it does to lower the barrier in the forward reaction, it lowers the barrier by the same amount for the reverse reaction. So in fact, adding a catalyst, and this is something then just to remember because you're always going to use the same answer, adding a catalyst does not affect chemical equilibrium. Adding a catalyst does not affect chemical equilibrium. All right? Why do we use a catalyst? Because it makes the reaction faster, which means that we reach equilibrium more quickly. But as far as the actual amount of product that we get out, whether we have a catalyst there or not, doesn't make any difference. But if I'm producing a product, I'm interested in producing it per unit of time and the amount of energy it takes to get it done. If it takes me 2 weeks to get my product, and I'm tying up my plant for 2 weeks to get a certain amount of carbon dioxide and hydrogen produced, that may not be very economical. If I use a catalyst, I might get the whole thing done in 2 hours. And if I can do it in 2 hours, even though it's not any more than it was before, but if I can do it in 2 hours, I can do 12 batches a day for 14 days. And that greatly affects the cost that my product is going to have to be sold at to be profitable. So catalysts are very important in the industry, not because it affects the amount of yield that we get, not that it affects the amount of product that actually is formed by equilibrium, but the fact that we get there quicker. So, a catalyst causes no change to equilibrium. There's nothing the system can do about a catalyst. It can't throw it out, it can't use it up, it can't do anything with it, and by Le Chatelier's principle, if it can't do anything, it's not going to affect the equilibrium. Some hydrogen is removed. Okay, so we're going to go over here and we're going to decrease the amount of hydrogen. We might do that by, say that we had again a closed system and maybe we had a semi-permeable membrane. Hydrogen molecules are very small, that hydrogen could seep through. So actually hydrogen molecules could escape from the container. Well, if they escaped from the container, if we decrease this, once again by Le Chatelier's principle, Le Chatelier says that the system is going to try to replace it. Well, the only way it can replace it is to form more product. So it's going to shift once again towards the product side. Whatever we do, the system will try to do just exactly the opposite. Okay? Well, let's look at one more here, this one being an exothermic change now. We see energy is given off this time. This time it says, what will happen to the equilibrium if we decrease the energy? Okay, so we've got the energy now as a product this time instead of a reactant. If we were to somehow decrease the energy by cooling the system, so if I pull energy out, the system's going to try to put it back. And the only way it can put it back is to shift over and form more products once again. If it produces more products, it will give off more energy, and thus it will increase the energy supply that I am trying to decrease. Okay? Volume is decreased. if we had a system, if we had this system sitting in a cylinder with a movable piston, and we pushed the piston down to decrease the volume, is what we're saying, can the system do anything about it? Well, it can't make the volume bigger, but the thing to keep in mind is this. If I decrease the volume, if I push down and decrease the volume, what will happen to the pressure? Back to our chapter on gas behavior. What's going to happen to the pressure? It's going to increase. It's going to increase. So really and truly the question here is, if pressure is increased, what will happen? Well, if we increase the pressure, the system will try to decrease it. To decrease the pressure, the only way it can do so is by decreasing the number of gaseous particles. We look up there and we see how many gaseous particles on the product side. 1. How many gaseous particles on the reactant side? None. So if I wanted to decrease the number of gaseous particles, which way would we want the equilibrium to go? If I want to get rid of the gaseous particles, which way do I want to go? 4 more products or 4 more reactants? Reactants. Because if we go this direction, towards the reactant side, we're going to use up the SO2 gas molecules. We don't form any gaseous molecules on this side. We have a solid and aqueous solution. So by decreasing the volume, thus resulting in a pressure increase, we're going to shift the equilibrium from the product side back to the reactant side, meaning we're going to have less of these and we're going to have more of the reactants occurring at equilibrium. All right? Let's look at the next one. All right, if we remove some calcium sulfite now in the process, we're removing a solid. Keep in mind that if we're affecting equilibrium, we should be affecting the equilibrium expression. Do we include solids in an equilibrium expression? No. If it's not included in an equilibrium expression, in other words, if it's always defined as unity, whether we have a great big pile of this or a little tiny bit of it, it's still going to be called unity. And so removing it doesn't change its concentration. Adding it doesn't change its concentration. Adding or removing a solid is not going to result in any change to equilibrium. Now, we're going to remove some SO2. So we're going to decrease the sulfur dioxide. Is that going to affect equilibrium? Yes, because SO2 is a gas. And so if I pull some of that out, if I decrease its concentration, again, if I decrease it, the system is going to try to put it back. And the only way it can put it back would be to shift over and form more products. And so our equilibrium is going to shift toward the product side. Okay? The last one here, pressure is decreased. Well, that one we should be able to answer pretty quickly because we just answered part B. We said if the pressure is increased, it's going to move towards the reactant side. So quite obviously, if the pressure is decreased, it's going to move toward the product side. And of course, we could see that because if we decrease the pressure, the only way the system could bring the pressure back up would be to form more gas. And we see that the only side that has any gas on it is this side over here, the product side with the SO2. So if I decrease the pressure, the system will try to increase it, and it will increase it only by adding more gaseous particles. Okay? So it's going to shift towards the product side to give us more gaseous particles. Well, as we go along, we'll look again at a couple more systems of Le Chatelier's predictions, but I want to go on to talk a little bit about the quantitative aspect of equilibrium as well. We stated that the equilibrium constant is described as the concentration of products divided by reactants, and of course raised to their proper power if they do appear as such in the chemical equation. If the equilibrium constant has a value greater than 10, it tells us that when equilibrium is reached, there must be a lot more product than there is reactant. Or in other words, there's 10 times as much product as reactant when equilibrium has been reached. So if equilibrium constant is greater than 10, we say that the product side is favored at equilibrium. Means that we have a proportionately greater amount of products than we do reactants when this equilibrium has been reached. If the equilibrium constant is less than 1/10, we say that the reactant side is favored. In other words, very little of the reactant has actually been converted to product. Most everything is still in the form of the reactants. Now, we can look at that specifically to a couple of reactions here. For instance, if we take sulfide ion and dissolve it in water, sulfide ion will act as the base. It will accept a proton from the water and form this HS minus, and we're left with hydroxide ion. And if we wrote the equilibrium expression, we would write the concentration of HS times the concentration of OH minus divided by the concentration of S2 minus. Remember, we don't include the liquid water. If we do this, we'll find in a table that this has a numeric value of 0.14, or 1.4 times 10 to the minus 1, 0.14. So, it's not greater than 10 by any means. It's not less than 1/10. So it's sort of an in-between number. In other words, it means that we have an appreciable amount of products. So we're going to have quite a few HS and OH minus. But we're at the same point going to have a fair amount of sulfide ion. So we're going to have fair amounts of all three of those species at equilibrium. One side or the other is not predominantly favored based on that numeric value. It's in between these two. Okay? Let's look at another acid-base reaction. Lactic acid. We talked about lactic acid in the chapter on acids and bases. And lactic acid is the acid that we find in milk from lactose. Lactic acid reacts with water. The acid donates a proton to the hydrogen or to the water and forms hydronium ion. Typical acid-base reaction that we wrote back in chapter 5. And leaves us the anion of the acid, the lactate ion, which I have abbreviated. There is no such thing with a chemical formula of LAC. That's just a short way of writing the lactate part of the molecule. Again, we would write an equilibrium expression of lactate times hydronium. Again, let me emphasize that it's multiplied by, not a plus sign in the equilibrium expression. Concentration of this multiplied by the concentration of this divided by the concentration of the lactic acid. Now, when we look at this equilibrium, we see that it has a numeric value 1.4 times 10 to the negative fourth, which means 0.00014. Well, we obviously see that that is considerably less than 0.1, which means that the reactant side is favored at equilibrium, meaning there are only going to be a few hydronium ions and a few lactate ions present, but most of the acid is going to be in the form of the molecular compound, the lactic acid itself. Well, remember we said weak acids were things that had very little ionization in water. This just numerically shows the amount of ionization they have in water. Strong acids, we said, are 100% ionized in water. They're going to have very large K values. Matter of fact, the K value for most strong acids is greater than 1,000. And we don't even put it down. We just call them large. We don't even write the number. So if I put in 1 mole of hydrogen chloride, almost the entire mole of hydrogen chloride will have gone to form hydronium ion and chloride ion, a strong acid. If I put in 1 mole of lactic acid, only a small amount has done this. The major amount is still as molecular lactic acid. So we see this number is much less than 0.1, meaning, in fact, that the reactant side is favored. It's not going to go very far before the reverse rate catches up and it reaches equilibrium. This one is an example of a precipitation reaction. Here, now, we're dumping a solution that contains lead ion into a solution that contains iodide ion, and we form the compound, the solid lead iodide. Now, again, keep in mind that for solids, we don't disregard them. We call them unity. So we had the 1 divided by the lead concentration and the iodide ion concentration squared. So there's our equilibrium expression. Look at the numeric value, however. 1 times 10 to the 8th. That's a whole lot bigger than 10. And it means that the product side is greatly favored before equilibrium has been reached. What that tells me is that if I dump these two together, almost all of these are going to have gone to the product lead iodide. I'm only going to have a very few lead ions and iodide ions left in solution when equilibrium has been reached. Almost all of it has shifted to that side. Now, let's take a quick look here at how we go about calculating equilibrium constants. This is something, of course, that has to be done experimentally. Let's suppose that we were to take some solid copper sulfide and dump it into water. We let the dissolving process go on until we're comfortable that equilibrium has occurred. By that we mean it's still dissolving, but it's now only dissolving at a rate at which these things are coming back together and forming the solid again, or precipitation, so that the forward and the reverse rates have become equal. Now, if we can measure these concentrations by some manner, some analytical technique, we might be using, for copper ion, we might be using something that would measure the color, because copper ion in water is a blue color. And so by measuring the intensity of the blue and making some standards up, one could determine what the concentration of the copper ion would be. Well, let's suppose that we had done that and we found that at equilibrium, after this thing had stood for many days and we know it's at equilibrium, we found that we had a copper concentration of 2.4 times 10 to the minus 18. And further investigation showed us that the sulfide ion concentration was equal to 2.4 times 10 to the minus 18 also. And that makes sense, because for every copper ion that I get, if this is dissolving, how many sulfide ions do I get? 1. I mean, they're a 1-to-1 stoichiometric mole ratio. So if I get 10 of these, I'm going to get 10 of those in the process. So we see the two concentrations are the same, and of course that would be logical. Now I'm going to write the equilibrium expression for this. KEQ is equal to the concentration of Cu2 plus times the concentration of S2 minus, all over 1, but I'm not going to bother to write the 1 this time because it's in the bottom of the fraction and it's really not necessary to write it. And we don't include liquid water. Now, we want to calculate the equilibrium constant. We've got the numeric values and we know the ratio of them. All we have to do then is put in the numbers. So we have 2.4 times 10 to the minus 18 for the copper ion, multiplied by 2.4 times 10 to the minus 18 for the sulfide. We're going to end up with something times 10 to the minus 36, and 2.4 times 2.4 is 5.76, and we could only have two significant figures, so we would call it 5.8. So our equilibrium constant is 5.8 times 10 to the minus 36. What does that tell you about the solubility of copper sulfide in water? It's not very soluble, is it? Only a very, very, very small amount dissolved before the precipitation reaction caught up. And so this tells us that the reactant side is greatly favored at equilibrium, meaning that most of the material is going to be in the form of the solid copper sulfide at equilibrium. Now, because this is a dissolving process, a solubility process, we sometimes refer to this constant as a special little letter. We call it KSP. KSP. KSP stands for the solubility, or dissolving, product constant. Solubility product constant. Solubility, and it's the product of the dissolved ions, concentration times concentration. So solubility product constant. And so KSP is still a KEQ. It's just a KEQ for a specific type of system. Okay. Now, the reverse process of this that we looked at a moment ago, where we had a precipitation, lead ion with iodide ion to form a solid. Sometimes we use the symbol K, PPT, to talk about an equilibrium that involves precipitating, forming an insoluble solid. Again, even though we're using different subscript letters, they all still mean the same thing, equilibrium constant, okay, KEQ. In our next lecture, we're going to look at some equilibriums with acid and bases. I'm just going to mention that now. We've got some more things to do with this type. But we're going to talk about Ka. You can guess what that stands for. Equilibrium constant of a weak acid. We're going to talk about Kb, equilibrium constant for a weak base. So we use little subscript letters to identify the type of chemical reaction that we're specifically dealing with, but they're all still KEQs only for those particular types of chemical reactions. All right, well, let's look at another solubility product calculation here. Let's suppose that we dissolve some silver sulfide in water, and we get silver ion and sulfide ion. in the process. Again, solid silver sulfide plus the water to give us that there. At equilibrium, we find that the concentration of the silver ion, by measuring it, was 5 times 10 to the minus 17, and the sulfide was 2.5 times 10 to the minus 17. Now, notice the relationship between those two for a dissolving process. Well, we see we get twice as many silvers as we do sulfides. So it would make sense that if silver is 5 times 10 to the something, that the sulfide would be half of that amount, or 2.5 times 10 to the minus something. We get 2 of these for every one of those. So if we get 10 of these, we're going to have 5 of those, and so on. So we have now our measured quantity for the concentrations. Let's write the equilibrium expression. This is a dissolving process, so we'll just go ahead and call it KSP right away. KSP is going to be equal to the concentration of the silver ion. Notice that it's not a 1, it's a 2, squared times the concentration of the sulfide ion. Again, we won't bother to write the 1, and we're not going to include liquid water in the bottom terms anyway, so that's all we have to write down. So all we have to do now is substitute in then our 2 values for our 2 concentrations that have been measured at equilibrium. Well, if we do that, then we're going to substitute in for the first one there, 5.0 times 10 to the minus 17. Put brackets. We must square that one. That's squared based on our equilibrium expression. Multiplied times 2.5 times 10 to the minus 17. Okay, so now all we have to do is the math. Well, let's see. We're going to have an answer of times 10 to the minus 51. And let's see, we're going to have 5 squared would be 25 times 2.5 would be 50, 62 and a half, 63 times 10 to the minus 51, or we would probably rewrite that as 6.3 times, actually it should be 62 because it's one of those exact 5s. It would be 62.5. And seeing that we're only using 2 significant figures, we would keep it as a 2 and drop the 5, not round up as I did. So 6.2 times 10 to the minus 50 for value. Is that what you got on the calculator? Okay. Okay, 6.2 times 10 to the minus 50. Look at the magnitude of this number, 10 to the minus 50. Quite obviously, this material, silver sulfide, is not very soluble. By the way, remember I said that we could have written products or reactants over products instead. But if we looked at this reaction and said, what would we have done if we would have been going that direction? Well, we can calculate the numeric value of the reverse, because KPPT, which is a reverse reaction, would merely be 1 over 6.2 times 10 to the minus 50, which would be equal to about what? 1.3 times 10 to the 49th. Positive 49. So if I ever get any silver ions in the presence of sulfide ions, I can pretty well expect that they're going to react to form solid silver sulfide and not leave a whole lot of the ions left behind. Okay? So KPPT is always the inverse of KSP values. We don't have charts of both KSPs and KPPT values because of this inverse relationship. We have charts of KSP values, and anytime we want to deal with a precipitation reaction, all we have to do is take the inverse of the number, and we have our value for the equilibrium constant for the precipitating reaction of the same materials. Okay. Now, a little different aspect. Let's suppose that we're given the KSP of a material, and we're asked the question, how many moles of barium chromate will dissolve in 1 liter? I might want to know how much barium chromate will dissolve in 1 liter. Well, first thing I'm going to do is I'm going to write the proper chemical equation. So barium chromate solid reacting with water, dissolving process. Notice we use a double arrow when we're talking about equilibrium. So we're showing both forward and reverse reaction as being possible. Previously, we've typically used just one arrow, meaning that things were going to the products, period. We didn't worry about equilibrium. But in this chapter and in the chapter 13, we'll see this double arrow used, just indicating then the equilibrium idea. We're going to get barium ion, aqueous, plus chromate ion, aqueous. I can write an equilibrium expression for this. KSP is equal to the concentration of the barium ion. For some reason it doesn't want to write on this one too well. Chromate times the chromate ion concentration. And not divided by anything because barium chromate is a solid and the other is liquid water, and we don't include either one of those in the expression. Now we have to think about this. Oh, we know one other thing. We can add, this is all numerically equal to 1.2 times 10 to the minus 10. That was given to us in the problem. The question is, how much barium chromate will dissolve? How many moles per liter of barium chromate will dissolve? That's the question. Well, when we have something we don't know, we often define it as what? What? Well, yeah, it's as an unknown, but what symbol do we sometimes use for unknowns? X. X is a thing that we often use. If we don't know something, we say, well, let X equal this thing that we don't know. So if we say here, let X equal the moles per liter of barium chromate that dissolve. Now, if X equals the amount that dissolves, let's go back up to our equation here. Let me ask it this way first before we put in the X. If 1 barium chromate dissolved, what would the concentration of the barium ion be? How many barium ions would I get? Let me ask it again. If 1 barium chromate dissolved, how many barium ions? This is not tough. 1, thank you. I mean, that's what the equation tells us, right? If 10 dissolve, we get 10. If 1,000 dissolve, we get 1,000. If X dissolves, how many do we get? X. Ah, yes, we've got it then. So now we can say if X is the amount that dissolves, then at equilibrium, the concentration of the barium ion must be equal to X. And the chromate ion concentration, well, I don't know. One of those days when things just aren't going to work, I guess. The chromate ion concentration is also going to be X, because we get not only 1 barium, but we also get 1 chromate for each one. Well, now you see, we can substitute these two values in for our equilibrium expression. And if we do that, we're going to have X now for the barium ion, X for the chromate ion, and that has to be equal to 1.2 times 10 to the minus 10 know if one of these others will work. Anyway, we're going to end up with now x squared is equal to 1.2 times 10 to the minus 10. Well, we might say, so what? Well, let's go back. What was our question? How many moles per liter dissolve? How did we define that? We said let x equal the moles per liter. If we can numerically find a value for x, we've answered our question. Right now we have everything listed, and the only question I have left is what do I need to solve this now to get a value for x? Remember, we can do anything to an equality we want to as long as we do the same to both sides. I heard somebody say it. Let's take the square root of both sides. If I take the square root of this one and take the square root of this one, the square root of x squared is x. And x will then become equal to 1.1 times 10 to the minus 5. One of the things I suggested at the beginning of the course, that you have a calculator that has a square root function on it and a square function on it, and here's one of the places where we're finally going to get to use it. X is equal to 1.1 times 10 to the minus 5 moles per liter, and that is the answer to our question. Our question was, how many moles will dissolve in 1 liter? X is moles per liter. Now, solving for x may not always be the answer. That might not be the final step. It may be that the answer is some multiple of x, depending upon what ion we're looking at, etc., in the system. But that's the way we can go about using equilibrium constants to actually determine the amount of solubility of a substance. Let me set one more up here real quickly. Calcium fluoride has a KSP value 3.9 times 10 to the minus 11. We want to calculate the molar solubility. Of calcium fluoride. Okay? Now again, the first thing that we would need to do then would be write a chemical reaction. Calcium fluoride solid plus the water. Equilibrium arrows gives us calcium ion and 2 fluoride ions. Now I'm not writing the aqueous, but they're there. It is aqueous. It's a water solution. All right? Now, we can say KSP is equal to calcium ion times the fluoride ion squared. We have to keep our stoichiometric balance from the equation in mind. We have to use the proper coefficients on expressing the concentrations. This again is unity, and we don't include the water, so we don't have either of those in the equilibrium expression. This whole thing is 3.9 times 10 to the minus 11. Now again, our question is, what is the molar solubility? So again, we could say, let X equal the moles per liter that dissolve. Now I'll ask the question again before we do the X. If 10 calcium fluorides dissolve, how many calcium ions do I get? 10. If 10 calcium fluorides dissolve, how many fluoride ions do I get? How many? 20. Because we get 2 of these for every one of those. If X calcium fluoride dissolves, how much calcium ion will we have? X. But how much fluoride ion will we have? 2x. So we want to keep that in mind when we bring it down here. We're going to put in for calcium now, X For the fluoride, we're going to have 2x is its concentration, but its concentration must be squared, so we have to keep that subscript, is equal to 3.9 times 10 to the minus 11. Now, if we do our math here, we're going to end up with 4x cubed. 2x times 2x would be 4x squared multiplied by x, 4x cubed, is equal to 3.9 times 10 to the negative 11. To get our answer, once again, we must solve for the value for x. Well, the first thing we could do is we could divide both sides by 4, so x cubed would become equal to 3.9 times 10 to the minus 11 over 4. And then in order to solve this, we would need to do what? Take the cube root of each side of the expression. Not the square root this time, the cube root of each side. Well, again, probably most of your calculators, having walked by and watched you do tests, most of your calculators have probably cube or cube root functions on, or multiple root functions, so you could go ahead and plug it in. If not, you could make up an approximate answer. If we did this, we're going to have something about 1 times 10 to the minus 11, and I'm going to rewrite that as 10 times 10 to the minus 12, and the cube root of 10 to the minus 12 would be 10 to the minus 4, and I would be asking what number times itself 3 times would give me about 10. Well, I note that 2 times 2 times 2 is 8, so my answer should be something about 2.2 times 10 to the negative 4th. Now, of course, you could get the exact number from your calculator. Now, is this the number that we want to put down, however? Well, what did we say? We said let x equal the moles per liter of the compound that dissolved, and so yes, this is in fact the answer that we would want. This is the molar solubility of calcium fluoride in water. Okay? I wanted to look back here and point out one other thing. Notice the KSP value for calcium fluoride, 3.9 times 10 to the minus 11, and quickly notice the KSP value for barium chromate, 1.2 times 10 to the minus 10. This has a more positive KSP value. It's a larger KSP value. Would make one think that maybe barium chromate is more soluble than calcium fluoride. But you can't look at only the K value, you have to look at what kind of compound. Notice the molar solubility of barium chromate is actually 10 to the minus 5th. The molar solubility of calcium fluoride is 10 to the minus 4th. It is 20 times more soluble than was the barium chromate in the previous one we calculated. So one has to be cautious on looking at KSPs to say which is most or least soluble. Okay? All right, we'll continue on and look at some equilibriums involving acids and bases in our next lecture. We've been talking about Le Chatelier's principle and the fact that if we have a system at equilibrium and subjected to a change, it shifts in such a way to try to alleviate that change that we've made, if at all possible. What I want to do here is just show a little demonstration of applying Le Chatelier's principle, making a prediction as to what's going to happen, and then in fact demonstrating that effect occurring. If we have a solution which has in it a chromate ion is yellow in color in solution, and a mixture with also some dichromate, this species over here, and it's orange in color. We'll be able to observe then this change in equilibrium if we subject the system to to some particular changes. And of course, obviously, the one thing that we can change in this system is the amount of hydrogen ion. Remember that changing the water shouldn't affect the equilibrium because, as we've seen, water does not appear in the equilibrium expression. So we will start here then with a solution which contains now only the chromate ion, and so we'll see that we have then a nice yellow color showing up for the chromate. Now, as we can see from the chemical equation and applying Le Chatelier's principle to make some prediction, if in fact we were to increase the hydrogen ion, it should shift the equilibrium toward the product side, increasing the amount of dichromate, or the orange species, and decreasing the amount of the yellow species. So we'll take a look and see if in fact this occurs. So I have here some nitric acid. A nitric acid is a strong acid, so it gives us hydrogen ions and nitrate ions. And I'll go ahead and then add a few drops of the nitric acid. When I first put it in, you can already see then some orange color appearing. We're beginning to shift the equilibrium in that direction. We'll stir this a little bit. We'll add a little bit more. We've added about a total of 6 drops. And now you can see that we have a solution which is fairly orange in color, in contrast to the solution we started with, which was very yellow in color. So we have predicted that by adding H pluses, we're going to get more of this. We see that is in effect occurring. Now the question is, if I could decrease the hydrogen ion, then the equilibrium should shift back in the other direction, giving us back the yellow species. Well, the question is, how can I decrease the amount of hydrogen ion? Well, if you recall from Chapter 5 when we talked about acids and bases, if I were to add some hydroxide ion would react with the hydrogen ion and decrease it. It would make more water, which doesn't affect the equilibrium, but it would decrease the amount of hydrogen ion. And so I have here a bottle of sodium hydroxide, and that's going to add now some OH ions in here. And so without moving this, I'm just going to draw a little arrow here. We're going to add some hydroxide ions, and of course this will form H2O. And in doing so, we are going to decrease now the hydrogen ion concentration. So let's go ahead then, we'll start adding a couple of drops of this. We've added 6 drops and stirred. Maybe need another 1 or 2. Actually, I've put about 4. And we can see now that the solution has gone back to the nice yellow color that we had for the chromate ion. So we see that by changing one of the reactants in the system, we have shifted the equilibrium first to favor the product side. Then by changing the concentration again, we've now shifted the equilibrium back to favor the reactant side. One thing about equilibriums is that they can be shifted back and forth a number of times. So if we put about 10 drops or so back in there of the hydrogen ion, Le Chatelier's principle tells us it should shift to the right once again, and we see that it has done so. If we put some base back in here again and stir it, we see that the orange color disappears, and we've gone back to the yellow chromate ion. This is one of the ways, of course, now that we can observe actually equilibrium shifting, and applying Le Chatelier's principle, we can see the chemical system actually shifting from one side to the other in accordance with the predictions that we've made.